All right, hey, welcome back everybody, and we'll get started. As you know, I said last time after the test that this chapter 23 is a long chapter, and so let me dive right back into it. It's all on Faraday's law, and of course a component of that is Lenz's law. Let me put that on the board to get us started, but we'll start with section 3. Actually, what I will do is kind of go back and do 3 examples from sections 1 and 2 that we talked about here, and then we'll continue on. But I want to keep saying this. I know it doesn't always seem this way, but physics really is about knowing just a few fundamental principles to explain a universal phenomenon. And so this whole chapter has one simple principle. It's called Faraday's law. Let me put it back here on the board. I'll come over here and say, okay, here is Faraday's law. And Faraday's law says that an EMF is equal to, and so you might recall we had this long discussion about what is flux and the change in flux, and how this negative sign is really going to give us the direction. And so we talked about how the Lenz's law says that you oppose the change in flux. And so we have this primary and then this secondary. I'm going to take this 2 steps further today and say, here was kind of my discussion yesterday. I was saying, let's ignore the negative sign and just talk about the magnitude of the change in flux, because the negative sign helps us with direction, but that was that whole discussion. In fact, maybe I will put that picture back here, because it's probably the most challenging part of this chapter is this picture that we were doing here, where we took a magnet and I took a north pole and moved it into a coil, and then took a north pole and pulled it out of the coil, and in both cases asked which way did the current move in the coil, which way did the induced current move. And so we had this primary field and then the secondary field. And so the secondary field is the current created here that opposes the change. Anyways, and then we did the south pole, and we did both going in, and then we said, let's pull it out with your author's piece of it. I think we talked about it, here too. Here we just didn't really talk about direction as much as there was this induced EMF. But like I said, we'll continue to talk about Lenz's law over and over again, because figuring out the direction can be a bit of a challenge. And so that's why we're going to break a problem into 2 pieces. The first piece is, what direction is it? And so we'll just say it opposes the change in flux. We'll call that Lenz's law, and we'll figure out what direction the induced EMF is, or the induced current is. And then the other part of that, we'll actually do a calculation, which we haven't got a chance to do yet, but that's where we'll pick up and say, okay, what is the value of that EMF? And so that's where I want to pick up here today. So that's one step. And I want to take even a step beyond that, because going beyond this textbook and recognizing that this class is a little bit above this book, but not as high as that university book. You know how I keep kind of bouncing back and forth and give you some of those hard ones. Let's throw some calculus in here, because if you take the limit as the change in flux, or the limit as time goes to 0 of the change in flux, you could think of this then as a derivative. Oh, this pole a little bothersome. All right, I'll take it down. I'm going to use it in a quick second. But we have the number of turns times the derivative of the rate of flux. And so if we have the benefit of calculus, let's do it together again. And so hopefully we'll kind of work out all the calculus for you. And other than the university book, we won't have to worry about actually doing the calculus on the homework or on the exam. But it's nice to see the calculus in action here. All right, so let me put a box around this, because as I was saying many times yesterday, I'm going to say today, you're going to see this over and over again. All 12 sections of this chapter are about changing the magnetic flux in some way or another. And when you change it, then it induces an EMF. And an EMF, well, that produces perhaps a current if you have a circuit. Okay. So I thought maybe a good example going back to section 1 would be problem number 2, and then also problem number 3, and also problem number 9. And that's where I was really hoping to kind of have stopped yesterday, was to do section 1 and 2 and these examples. But picking up here today, let me jump to the end of the chapter. I wrote it down with page 1052, and say, let's take a look then at problem number 2, and I'll make it a little bigger here for the screen. And so problem number 2 says, what is the value of the magnetic flux through the coil in figure 56? So here's figure 56 right here. B. All right, so this was the part I was lecturing yesterday. You've got to visualize these magnetic fields, which is why, in order to do this chapter, you have to significantly understand last chapter. So it was good that we had an exam on that last chapter, because I know that made you study deeply that last chapter. And one of the things we learned in the last chapter was called right-hand rule number 2. And so this wire right here with the current going up probably looks a little bit like a test problem. We had a wire going up, and you had to calculate the force on an electron that was moving. And so to recognize that, you had to recognize that next to that electron was a wire that then made a magnetic field. And so that's what I'm trying to say. You can't see the magnetic field, but this wire, if you grab it with your right hand, thumb pointing up, and the magnetic field would be then the direction of my fingers. So on this side of the wire, so the left side of the wire, the magnetic field's coming out of the screen. It wraps around, so over here in front of the screen, the magnetic field, or the flux, is going this way. And then this side is going in. So this was where the coil is, and so that's my question. And so I'll hold this and say, okay, it's saying how much flux goes through here. But if you'll notice, the picture is, I think, trying to show the coil in this position. And so no flux goes through it. That's what they want you to visualize. They want you to say, kind of like a shadow. Where's that little piece of wood I was using? If I put this up here and you look at me blocking the light and you look at that shadow, that's sort of the same direction as the light is the same direction as the flux here from this wire. So if I turn it this way, you'll see the shadow is getting less and less and less and less and less and less, and that's about as small as I can make the shadow. That's blocking the least light. And if this was infinitely thin, it would block no light, because it is kind of flat. Or put another way, in our calculation, we would have cosine of 90 degrees. And so remember, the calculation for the amount of flux depended upon the strength of the field, the area of whatever the object is we're talking about. In this case, it's the coil. And then the orientation between those two. And in this case, the orientation would be 90 degrees, and cosine of 90 degrees then is 0. So that's the whole point, really, here of problem number 2, is to help you visualize the flux. That's what we did yesterday. I think number 3 is a lot like this. Let me scroll down to the next page here. It says, referring to figure 57, what is the direction of the induced current in number 2? Okay, so we're looking here at figure 57A, this one. I think your homework problem is to look at this one. So you got the wire in the coil. But here we have two coils adjacent to each other. And the question is, what is the direction of the induced current in coil number 2? A, if the current in coil number 1 is increasing. All right, so let me say it again. This is what we meant by Lenz's law. The direction of the EMF, or the direction of the current in the secondary, that's that second coil, is how the flux is changing in it. It opposes the change. So let's run through this again, and my point is find out what direction the flux is initially, and then figure out what it's becoming. And so the flux has to make up for that change. It opposes that change. It wants to go back to the original. All right, so here's my thinking. So here's coil number one. Coil number one is making a current in a, from our vantage point, looking in here on the screen, this is a counterclockwise direction. So if I were to take a ring and hold it right here and say, okay, the current is going in a counterclockwise direction. And again, if you remember from right-hand rule number 2, holding the ring with your thumb in the direction of the current, we would get magnetic flux coming out of the ring, looping around, and in this case going through coil number 2 and coming in behind it. And so what's important here is to say that the flux in coil number 2, which is coming from number 1, is going in. So we have flux in. And then it says the current in coil number 1 is increasing. So that would make even more flux. The flux is created from the magnetic field, and the magnetic field is created from the current. So again, we got to go back to the last chapter. Where does the magnetic field come from? Moving electrical charges, right? Hopefully you got that one right too on the multiple choice. All right, so that's where it comes from. So if we're going to increase this current, we are going to be talking about a situation like this, where the flux, and this is where kind of that mental picture has to come into mind, said it's going in. And what's going to happen is I'm going to get even more in. So Lenz's law says that the current will be set up in this secondary in such a way that the flux created from this secondary will oppose the change. So opposing the change means to make flux come out, to subtract it off. If I put some numbers here, let's say our flux going in was 10. And as the current goes up, it's trying to get up to 12. But the current in here is trying to oppose that change. It's trying to keep it at 10. And so in order to do that, it's going to make a 2 coming out, right? Because if you've got now 12 going in because of this coil, and then you make 2 coming out because of the secondary, you're back to where you started. You're back to the original. That's the key to these. Get back to the original. Oppose the change. So if you had 10 and it's going up to 12, you need 2 coming out. And in our case, we're not actually dealing with the numbers. We're just saying what direction. And so I'm just trying to say it's going to be coming out. And that's the key you need to know. The key you need to know is it comes out. Yeah. Okay, so again, all right, and again, listen carefully to primary and secondary, because there's 2 fields going on and they can drive you crazy if you mix them up. Okay, so there is a field from coil 1, let me call that the primary. Then that's going to induce a current in number 2, so that's a secondary. All right, so the total field wants to remain the same. So when we take coil number 1 and it has a current making a flux in number 2 going in, and let's just say it starts with a total of 10. And so we're getting 10 from the primary, and somebody turns up the current in the primary, so it goes from 10 to 12. The current in the secondary wants to make a flux coming out so that the total, the 12 coming from the primary, and now the 2 coming from the secondary, gives me back to a total of 10. Okay, so that's how my thinking is going to know that I need to say the current needs to be set up in coil 2 so it comes out. So it opposes the change.
In, because I thought when we did
Okay, so, and so you guys on camera, she's asking about the direction of the flux. And primary one, the flux is coming out in the center of the coil. That's what you're thinking of. But then it wraps around and goes in outside the coil. So I think what you're focusing on is last chapter, we always focused our attention on the flux that is inside the ring. But this problem is outside the ring. So the magnetic field comes out here, hooks around, and comes back in. So, yeah. Well, good, and I'll say it again because you're nailing it right on the spot, that in order to see this, you got to see which way is the flux from the primary, and then you got to see which way it is changing, either an increase or a decrease, before you can then figure out which way the flux is supposed to be in the secondary, which then eventually gets you to the direction the current is supposed to be in the secondary. So there's quite a few steps there. And you have to remember it opposes the change, it doesn't oppose the flux. All right, so if I kind of start this again, I would say, all right, so here's the primary, it's got some current. In the ring, it's coming out, but it loops around, and so in coil number 2, it goes into the screen. And since part A says the current is increasing, there would be more and more going into the screen from the primary. Therefore, the secondary is going to make flux coming out. That's the key step. Because once you realize the direction the flux needs to be in the secondary, you can go back to the last chapter and say, all right, what direction would the current be in a ring in order to come out? And that would be in a counterclockwise direction. And so this should be counterclockwise as the current in coil 1 is increasing. Now, same logic, different results, but same logic, let's try B. B says, if the current in coil 1 is decreasing. All right, so coil 1, the flux comes out and wraps around, so nothing has changed there, so the flux is going in. And let's just say for a number, let's just say it's at 10, whatever the value is, it's 10. But now you're decreasing the current here, and so that means you would have a decrease in flux here. So instead of being 10, it's going to maybe drop down to an 8. Well, to make up for that, because we want to stay at 10, that's what I want to emphasize. We want to get back to the original. So if this one now is decreasing its flux, so if the primary is decreasing its flux, the secondary is going to make up for that. The secondary then wants to make 2 going in, so that the total is back to the 10 that was in. We always want to get back to where we started. It opposes that change. Okay, so to get back to 10, we got to have it going in. Now to go in, go back to last chapter, we would have to have current going in a clockwise direction. And so B, the direction would be clockwise, which is the opposite of what it was in A. And that's again like we saw with these experiments where I move the magnet. Is this thing still hooked up? I guess not. But current goes one way, and then it goes the other way. And so it's the change in flux. We always want to focus our attention on the change. Yeah?
I want to make sure I understand this correctly. So if, I guess in this case, a coil, another coil in the system, specifically the primary, if that changes, then the second one, its reaction is to change magnitude and direction?
Well, its reaction is to keep the flux the same. That's Lenz's law. Opposes the change. So the current will be set up in the secondary in whatever direction is necessary to get the flux back to what it originally was. And so that's why when we turn the current up, we get a counterclockwise direction to this. And when we turn this current down in the primary, it goes the other direction. Wants to keep it back the way it was. It opposes the change. All right, well, like I said, these can be pretty tough, and I'm glad we went through a lot of these. Let's try number 9. Here now, I think is actually a chance to do a calculation. Here it says an MRI technician moves his hand from a region of a very low magnetic field strength into the MRI scanner, which has a 2 Tesla field, with his fingers pointing in the direction of the field. All right, so just for the sake, I'll use my hand, and I will just say, let's say that the field is going, say, into the screen. Okay? Because he says he moves his hand with his fingers pointing in the direction of the field. So if I were to take my left hand here and move it into the field. So I'm outside, I move it into the field. Okay? And I do it in such a way that my fingers are pointing in the same direction as the field. So if the field is going into this screen, my hand would go like that. I reach into the machine maybe to adjust something. All right. If the average EMF, find the average EMF induced in his wedding ring, given that the diameter is 2.2 centimeters, and assuming it takes a quarter of a second to move into the field. All right, so now we can actually do some numbers. And so let me calculate the magnitude of the EMF. All right, and I'll go ahead and switch back from the calculus form to just the algebra form, a change that's kind of an average effect, and that's what they said, find the average. But I'll start with the n and say, okay, now n is the number of turns. I'll ask you how many that is in just a second, but I'm going to replace the flux with our discussion from yesterday. Remember, the flux is a combination of 3 factors, right? It's this visual effect of how many aligned. If you were drawing pictures of the magnetic field going through a square, you would say, how many lines are you drawing? So it's a combination of how strong is the field, how big is the area, and the orientation of that. Those 2. Okay, so I guess I would start with, say, there's only one loop. It's one ring. It goes around. It's not like this one here where I had said if I only had one loop, I'd get a small EMF, and it wasn't enough for us to see much, so I went ahead and used this coil that has 3,400, and that amplified it by 3,400 times, because you get the same EMF for every loop, and so you make a bunch of loops. But a wedding ring would, of course, just have one loop, just goes around once. All right, so there's the easier part, the N. The change in the magnetic field is, I think, fairly simple, because you might say it's, final minus initial. And I'll say the final is 2 Tesla. The area, I'll calculate the area in just a second, but let me say it's pi r squared. Let's talk about the angle here also, but I just wanted to take a moment to say, since it is a change, I have to go final minus initial. And initial is what I wanted to get here on the board. See, initial, they said, the technician is outside of the field. There is no field, so the field is zero. So the flux is zero. And so remember, the flux depends upon those three factors. How strong is the field, how big is the area, and what is the orientation of the two. And so if I use this bigger ring as the wedding ring, and I use this light coming in as kind of the electric field, I guess I would start with it outside of the field and say, well, how much light, how much field is going through here? Zero, so that's initial. But then final, you can see that if I hold it in this orientation, I get a lot of light that goes through there. And of course, if I rotate the ring right there, I would get cosine of 0. Or cosine of 90, which is 0. Yeah, that's all right. But they had the technician putting their hand this way, so the orientation is important. And so here's the orientation, right? And so remember from yesterday, we were using this helpful device to say what is the direction of the normal vector. All right, so we already know that the magnetic field is going inward. If I take this and kind of imagine putting it on the surface of this ring, you can see my little red pointer, my normal vector, is also going inward. So they're the same direction. So I guess I'd call that 0. The angle between them is 0. The field is going in and the normal vector is going in. There's no angle between them. And so this right here is 0 degrees. And cosine of 0 degrees is 1. Okay, now the other thing is I think they said this takes a quarter of a second. Let me come back and check a number here. Yeah, 1/4 of a second to move in. So let me put my numbers together and also my units. So my numbers would be 2 from the magnetic field. There would be a pi, and then I need the radius squared. And I think they said diameter. So I'm not going to fall for that. So the radius is 1.1 centimeters. Let me do my units kind of separate. And so that would be the magnetic flux. The area, the field, and the orientation. And then subtract 0, so that's the change in the flux. And all of this takes a quarter of a second. So there's the numbers. Now the units would look something like this. The field would be a Tesla. The area would be meters squared. And the time would be in seconds. So I'll start with my numbers. But this is a 2 times a pi times a 0.011 squared. Cosine of 0 is 1. I won't put that in my calculator. Then divided by a quarter. And my number here is 0.00304. And the units, I hope, since we're calculating an EMF, that's a voltage, right? All right, so I hope this comes out in volts. And of course, trying to remember what a Tesla is. Remember, a Tesla is the unit of the magnetic field. And the definition of the magnetic field is when you get a force of 1 Newton, when you have 1 coulomb of charge moving at 1 meter per second. That was our definition there of a Tesla. So then I'll have a meter squared over a second. And so these 2 seconds cancel off, these 2 meters cancel off. Then you have a Newton times a meter, which is a joule. So then I have a joule over a coulomb, which is the definition of a volt. Yay! And so just like you probably have seen me do a number of times in the little video answers I send out, you know, hey, let's go through the units. These are all new units. These are these Faradays, these voltage, these coulombs, Tesla. For most of you, this is all new. And we got to go all the way back to our chapter 1, and that what seemed so easy, changing units, I was trying to give you that pattern of how do we convert units and keep track of our units. So our unit analysis does work out right, so we're kind of happy here with the results. All right, well, like I said, there's a lot to cover, so I better keep talking. But we keep doing the same thing over and over again. So I suppose there's some good news there that we'll just keep doing. Faraday's law, Lenz's law. What can make it challenging, though, is we have to keep going back and incorporating the stuff we've learned in the past. For example, part B of this question, then, says something about the relevance of this EMF. I think it says, discuss whether this current would significantly change the temperature of the ring. So what essentially, if I could maybe draw a picture here, is we have now a ring, a wedding ring if you will, and it's kind of like there's a miniature battery in it. That's our EMF, right? This is how we started the chapter. We started the chapter by saying there's two ways of making an electric field. The first way is with a chemical, and this is what we've been doing up till this chapter, but the second way now is a changing magnetic field. And so we could kind of say that while the technician is moving his hand in the field, it's as if somebody has installed a little battery in the ring. There is a miniature EMF. Remember, electricity is made by moving magnets. Moving magnets make electricity. And so there would be a current set up here. And then we could do our I squared R from 2 chapters ago. And we could say there's a warming then of that ring, and that ring's going to warm up. It's going to get hot. However, I think without really doing any math, we can see the voltage is incredibly small. And hence the current is incredibly small. And it only involves during the transition. Once the technician is in there, there's no change. And it's just not going to be significant. I can't imagine it being significant. That would be a fun discussion if I knew somebody working as a technician in the medical field to ask them, does policy require you to remove all your jewelry, including your wedding ring, when you put your hand in there? And it wouldn't surprise me if policy said, yeah, we have to do that for different reasons, but this would be one of them. It's also a big magnetic field, so if any of it's magnetic, and most jewelry is not magnetic, so, so I don't have to worry about that. But you got to be concerned with, things like that. And so that would be an interesting question. And then ask somebody if they've actually done, have done it. I knew a friend in graduate school who worked in very large magnetic fields, and they would have to sometimes enter into the chamber. And it was this giant chamber, maybe about the size of my stage up here. And he said if you actually just walked at moving pace through it, you could feel a warming effect. And so their safety protocols had them step, stop, step, stop, step, stop. And for them to enter the chamber and do whatever they had to do while the field was on, it was, little precautions are significant precautions were taking place. All right, well, shoot, I better move on if we're going to get anything close to finishing this. Let's go to section 3. Your author calls this a motion EMF, but again, it's still the same idea. It is an EMF, but it's one of the best ones to really talk about first before we get to generators, because it, I think, gives a really good picture of what's going on, more than any of the other ones. This one's probably the easiest one to see, so it's a good place to start. And the author just simply says this: what if you took a metal bar and you laid it across 2 rails, And so imagine two metal stationary rails, and you got a metal bar laying across there, and you just move the metal bar. And so that's what that green arrowhead, it says move it with a velocity v. Also, though, and this is what the x's are for, there is a magnetic field going into the screen. So if there's a magnetic field going into the screen, then as this metal bar moves out, wouldn't there be more and more flux in this rectangle? And so remember, the change in flux, and so maybe I'll put it here, EMF magnitude is equal to N as the flux changes with time. And remember, the flux is the magnetic field, the area, or the angle. So since the magnetic field is made of those, anything that changes the magnetic field, anything that changes the area, anything that changes the orientation would then be a change in flux. And there's a lot of ways to change the magnetic field. There's not too many ways to change the area, but this is an example of the area changing. The orientation is not changing, but the area is. And so as this thing moves, and so that's what your author calls this a dx. All right, so let's do the two parts again. Let's do both the number and the direction. And a lot of times I think the numbers are easier than the direction. The direction is Lenz's law, so let me do the numbers first this time, all right? But even then the numbers aren't so easy. But I'm going to go ahead and say, all right, if I try to do this calculation, I guess the first thing I would do is say how many loops of wire do I have? And I guess I would say, well, just one. Okay, and so here is this one loop of wire. Notice the resistor here. Okay. Then I'll take the derivative, and to get the flux, I will say it's B. So that's the strength of the magnetic field. That's what's indicated with those arrows, or X's pointing inward. For the area, why don't I do this? It looks like if I say the bar is at position X, and of course it's changing, but I'll just say has some distance from here to here, I'll call that X. And then the length of this bar is L. I guess I could say the area then would be X times L, right? The area of this rectangular loop. Now, when it comes to the orientation, the angle, we need to look at the normal vector. So we got this little tool out here. If you can kind of imagine setting this on the surface here. And I suppose we could put it on the back side over here. If you put it this side, you might say that the normal vector is out and the B field is in, so you might call that 180 degrees. If you put it on the back side, you might call it 0 degrees. Either way, cosine of 0 or cosine of 180, its magnitude is 1. 0 is a plus 1 and 180 is a negative 1. But since I'm only calculating the magnitude, I'll just say cosine of, and I'll put it like I was holding it 180, but remember, I'm going to do absolute value. All right. So in terms of orientation, this is just a 1. So nothing exciting for orientation, and nothing exciting about the number of loops. But then let's look at this calculus. This calculus says take the derivative, and so as you study this problem, what's changing? Well, it's not the magnetic field. They're trying to indicate that the magnetic field is the same everywhere in this rectangular loop. That's why the spacing between each little x is exactly the same. Remember, we try to draw the strength of our field by how many lines we have. We did that first with electric fields. Now we've been doing it most recently with magnetic fields. So he's trying to indicate here that that's a constant number. Clearly the x is changing. That's the moving metal bar. But the length of the metal bar doesn't change, so I'll pull that in front of the derivative. And then you get a very simple answer that says for a motion EMF, the amount of voltage you get depends on these three factors. What is the strength of the field? What is the length of the bar? And how fast are you moving the metal bar? And hence, that's why we call it a motion EMF. So that's its magnitude. And so you could do something like this. You could say that what you have is kind of a built-in battery. It's like somebody magically put a battery in there. They didn't really put a battery. You didn't get an electric field from a chemical. You didn't get the electric fields from the charge. You got the electric fields from the other option, right? The other option is a changing magnetic field, or in this case, changing flux, because the area is getting bigger. So as long as something changes, either the field or the area or the orientation, one of those changes, you're going to get an EMF. Now, I should be a little careful, because I put the battery going in this direction, and I'm really not sure at this point whether the battery, now that looks kind of funny. I'm not sure which way to put the battery, because I haven't done the direction yet. All I did was the magnitude. All right. So I'm going to put right here that I have created a little battery, and therefore there's going to be a little bit of current. In fact, the current then would be the EMF divided by the resistance. This is the Ohm's law. And the EMF then is BLV over R. So if this question said how much current do you have, I can get it. I could put two pieces together. I could put this chapter together with Ohm's law. So this chapter, Faraday's law, tells me what's the value of the EMF. Then Ohm's law tells me if you take that EMF and divide it by the resistance, that tells you how much current is here. And that's what your author's trying to do down here in this picture. He's trying to say this is equivalent to having a little battery and a resistance. The little battery is coming from the electric field, which is coming from the changing magnetic flux. That's the conceptual picture here. Now, I guess I should try to explain this picture, because this picture says we've got this B and he's got arrows coming out. And then he's also got these areas going in. And this is where the picture can get confusing, because remember, there's a primary and a secondary, and it's easy to mix those up. So before I get to this second picture, let's just go back to the original where only you see the primary field. So let's do the harder one now. Let's do the Lenz's law. Let's do the direction of the current. All right, so as this metal bar is moving out, can you see that there's going to be more and more flux going in? I mean, in the picture they have right now, if you put the bar right here at this dotted line, you would say 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got 9 lines going in, 9 little lines we would draw. So we might call the flux 9. And then as it moves over, we get 3 more. So it's going from 9 up to 12. So there is an increase inward. The primary is getting bigger and bigger inward. So which way does the secondary want to be? Out, to oppose the change. We want to create a flux outward. So the total still goes back to the 9. So by the time you take the new value from the primary, which is now 12, and then you take 3 more coming out from the secondary, you're back where you started. Yes, that's the point of Lenz's law. All right, which is why down here in his second picture, he shows dots coming out. He's trying to say that the field from the current in this loop, the secondary effect, the induced current is coming out. So which way does the current have to be? And so here he has his right-hand rule number 2, and he's got the thumb pointing in the direction of the current so that the fingers would be coming out. And so clearly the current would have to go this way, which would answer our question, which way is this little battery? it is the way I originally drew it. And I'll tell you, I just got lucky there. I wasn't even thinking about what direction. I was just trying to say, hey, there's got like a little battery there, and I hadn't yet done the direction, but now I did. And so now I've done the math to get the numbers of the EMF, and I've done the math to get the current, and I can also then do the Lenz's law to get the direction. All right, well, how about we try number 17 as another example here? Because 17 is also a motion EMF. Although 17 is a little bit of a letdown, but I think it'll still be okay because it doesn't make us do Lenz's law, which is the harder part. It doesn't make us do direction. It just makes us get the voltage. So 17 says a jet airplane with a 75-meter wingspan is flying at 280 meters per second. What EMF is induced between the wingtips if the vertical component of the Earth's magnetic field is 3.00 times 10 to the minus 5 Tesla? All right, so let me just take this airplane here, okay, and it's flying along. That's a motion EMF. I've got a metal bar, wings probably made out of aluminum, moving through a magnetic field, and that's exactly what this is. So I think probably the hard part of this problem, if you saw it on a homework or a test, would be to recognize why there is an EMF. That's really the hard part. The calculation is not. The calculation just says, okay, well, the EMF we derived here in class is BLV. And all three of those are given, so it's just kind of a plug and chug like we've done on these other ones. So let's see, the field is 3 times 10 to the minus 5 Tesla. The length of the wing $75 meters. Okay. I guess this is a big passenger plane. Okay. 75 meters is huge. Okay. I heard jet plane and I was thinking like a fighter jet plane or something. All right. So, but big jet passenger airplane. Big 747 or something. I don't know how big it is, but probably in that category. 75 meters. Wingspan. It's flying at 280 meters per second. And so, like I said, the numbers isn't the hard part here. The hard part really in a problem like this would be recognizing, what do you mean? It's just an airplane flying. How does it become a battery? Well, it's moving in a magnetic field. Mm-hmm. All right, so 3 times 10 to the negative 5 times 75 times 280 means we would produce about 6.3, and since we did it on the last problem, remember this works out to volts. And so there's my volts. Not much. Consequence, probably not much. That's what it says here. You're going to get something like this. Let's say we're looking down on the top of an airplane. Here's the fuselage. Maybe here's the wings. I know we derived it as straight across, so maybe I should draw an airplane with wings straight. Back wings, tail, looking down. But being 75 meters across, then what's going to end up happening is there's going to be a movement of charges. Maybe electrons will build up over here, leaving a lack of electrons over here. Ultimately, that would create then an electric field, and the electric field would be pushing it opposite that the magnetic field wants to push them, and they'll balance each other. So eventually you'll get your E times D for your voltage from your electric field, and then nothing more will happen. So kind of boring. Can't use it for anything. I tried to hook up a wire to maybe run a light for my little passenger plane. Sadly, the electrons in that wire are doing the same thing, and so it's not a good way to kind of siphon anything out. There are some tricky things you can do. You could disconnect the wire from the airplane so it's not moving, and so as it flies through, maybe the electrons come off and the electrons circulate back through the atmosphere. So then you can actually make a little battery out of this. Works better if you're higher up in the ionosphere. And so I say that because that's one of the hopes that NASA has, that maybe they could just take the space shuttle, well, space shuttle's gone, but next generation or satellite, put a long wire on it, and just as it orbits around the Earth, could generate its own electricity for the mission. Or hook it on an orbiting asteroid and feed the energy off the asteroid. Anyways, so there is some kind of fun, interesting things that maybe could come from this. But for this one, it's just, I wouldn't say anything too useful. But like I said, it's a good one from an educational perspective because you can really see the change in flux because the area is changing. That's the easiest one to see. Now, perhaps a hard one to see is what we call eddy currents. Sometimes we refer to this as a braking effect. And the best thing I think I can do is kind of demonstrate it by saying what would happen if I took this pendulum, if you will. And so you can see I've got kind of this metal plate, and I've got it on some really nice bearings, so it goes back and forth really well. Okay. And this is going to swing for a long time. Not forever. Obviously, there's air resistance, and there's some resistance in there. But I want to convince you that it freely swings really well. But what happens if I take a magnet, strong magnet, and I want to point it to at least you guys here in class, and maybe you can kind of see it here on the camera. You guys are off at a little different angle. But if I pull this back, it's going to swing through without hitting the magnet. But do you see how poorly it swings? Do you see if I even just move the magnet without touching it, it moves with me? I haven't changed anything. It still swings really nice. And to kind of understand what's happening, you might see it start to take shape if I do the same thing, but this time I'll cut the aluminum metal piece down here at the bottom. And I'll kind of do the same thing. See, by itself, it swings really well. And if I send it through a magnetic field, it still swings pretty well. And so, what's the difference here? And this is referred to as braking, electromagnetic braking, or eddy currents. And your author does a good job in this next section. Section, I believe, 4 here. He shows this picture. Maybe this will be a better picture. But he's trying to say here that when you pull this back, and as it's falling, it goes from no magnetic field to big magnetic field. So there is a change in the flux. And the whole principle here is a change in flux then is going to make an EMF. It's going to make a current. Now, it's going to make what we call eddy currents. Maybe you're more familiar with that word when you see it in a creek or a river. In fact, maybe I should say if you're not familiar with it, I should probably point out, if you've ever seen a creek, you'll see something like the water flows down, maybe the water goes around a rock. As it goes around a rock, it makes kind of like a little swirl. That's an eddy current. And technically, there's part of the swirl that is going upstream, and so the little currents just go around in a circle. And that's what your author is trying to say. He's trying to say, look, watch what happens here when this metal piece goes from out to in. Okay? And the metal piece would be out here, no magnetic flux. Then when it goes into the field, and so we've got a field going inward, there's going to be some flux. So the bottom line is there's a change in flux. Anytime there's a change in flux, there's an EMF. If you have a voltage, an EMF with some metal wire, you're going to get a current. And so your author is trying to say, as this is entering, there's going to be a current. As it is exiting, there's going to be a current. The harder part is what direction is that current and what consequence does that have? So let's talk about as it's entering. So using Lenz's law, I would say when this metal piece is out here, there is no flux. And then as it enters, and then notice they've set up the field so it's going inward. Now that I think about it, how did I set up mine? Oh, good. So I set it up as inward, at least from this position. So this is the North Pole. This is the South Pole. So the magnetic field would be going inward. Okay. And so as it goes in, I would say from the primary, okay, the primary are these little X's going in, the flux is increasingly inward. So what direction does the flux need to be from the secondary? Outward, right? It opposes the change. We had 0, now we're getting a bunch inward, so it wants to make it outward, so the total is still 0. So which direction does the current have to be in the secondary in order to make the flux come out? So this is my pendulum. And as it swings in, current needs to be set up in these little circles, these eddy currents, in such a way that the flux comes out. And that would be a counterclockwise. And that's what he's trying to show here. Counterclockwise current is going to set up in here. Which, by the way, that's why this one didn't work. Because by cutting the metal pieces, we've interrupted the flow of the electrons. You don't get these eddy currents. Now you might say you get little tiny ones. Okay, so we get some, but we don't get nearly the number we get here. They've been interrupted. And so that's what this one's trying to illustrate, that there is a set of currents that goes on in here. All right, so this little set of currents is going around in a counterclockwise direction. But then what's the consequence of that? So remember, when this goes around, this too makes a magnetic field. This too makes a North Pole and a South Pole. So how does the poles here interact with the poles here? And so as this goes around, we said the flux comes out of this ring and loops around. It's as if this magnet with its North Pole is pointing out like that. So there's the north. And so as this current goes around, it's making its own magnet. So I call this a secondary magnet. So the flux from that one, the primary, creates a secondary current, and that secondary current creates a secondary magnet. And then if you think of this magnet with the North Pole out, how does this North Pole then interact with that North Pole? So now remember, this North Pole is over here. As I stand here, it's on my right. And I've got this thing coming in, and I've got a North Pole. Doesn't these repel each other? And the South Pole interacts with that South Pole. And so what I will call the secondary magnetic effect interacts with the primary magnet by opposing it. It blocks it. It slows it down. It's a braking effect. Exactly. And so that's what I keep saying. We have to understand Faraday's law with Lenz's law. And then all the stuff in the past, if we put that together, we get some very interesting behavior. And again, that's what this whole chapter is centered around. So this would be, as your author is trying to point out, a braking effect as it is entering. Now, as it is exiting, or maybe I should say in between, this one's got a small enough metal piece that there's a point where the whole metal piece is actually in the field. It's the opposite for mine. I've got a big metal piece on a smaller magnet. So there's never a time where all of my metal piece is in the field. But in your author's picture, there is a moment, let's say when it was swinging right here, where it was actually in the field. And in that case, there would be no change in flux. And so in other words, we have a braking effect only while it's entering. Of course, because Faraday's law says it only happens while you change. And so as this comes in, there's a change. Now, as it comes out, there's a change also. So let's talk about that one too. And let's start with Lenz's law. What direction would the eddy current be? That is the secondary. What direction is the secondary as it is exiting? Well, let me grab my marker here so I can write it on here. But I hope what you're seeing here is as it swings in, you have to remember that it already has a bunch of flux going in, and now it's coming out. So it's going from, say, 10 inward down to 0. Remember, Lenz's law says we oppose the change. So if we're got 10 and going down to 0, the eddy current in that one wants to make it so the flux is inward. It makes up for that losses. So what direction would the current have to be inward? Clockwise. There it is. And it kind of makes sense that the current on the exit would be opposite of the current when it enters, right? We said it enters, it would go counterclockwise, and so when it exits, it goes clockwise. Okay, all that makes sense. But I think what's surprising is it's still a braking effect. It's not now pushing it out, it's actually a braking effect, because if you again imagine, so here it is swinging out, the current now would go in this direction as it exits. Did I write this one wrong? Oh, this is an old one. Where did I write it? Oh, there it is. So entering. So entering, it went that way. Then exit, it went this way. Okay. And like I said, your first reaction might be, well, wait a minute, that's opposite current, sure. But it's not a push, it's still a brake. Because if you can imagine current going around this way, that means the flux would go in and circle around. So it goes in that way. If I grab my little magnet, okay, how would I hold this magnet so that the flux goes in? I guess I'd take the North Pole and put the North Pole in. All right. So when I get over on this side of the magnet coming out, I would have a north on the other side. It's near the south. So now they're attracted. But see, it's attracted as it's trying to exit, so that slows it down. So yes, things are reversed, but it's still a slowing down. So the current is reversed, the poles are reversed, all this in the secondary, but it's still a slowing down. And so whether it's entering or exiting, it's still a braking process, and it's still creating a current. And in case you're wondering, this is an excellent effect that they love to use for the electric car. And there's a lot of potential of growth here. They call it regenerating braking. But what you can do, instead of stopping an electric car like you do a gasoline car, or what we call it, an ICE car, an internal combustion engine car, that, like a bicycle, you just step on the brakes and the shoes come in and they make friction and rub and turn all the kinetic energy into heat energy. But wouldn't it be better if we could do some kind of braking where it made electricity and recharge the battery while you were stopping? And so you use the battery to get going, and then you charge the battery when you stop. Your battery would last much, much longer. You're essentially recharging it every time you brake. Now, obviously, you use a little bit more than when you brake, but as much as you can recover, the better. And so regenerational braking is awesome. And I have, let me go grab it. I had to put it on the charger because I realized this morning it wasn't charged, but I got a little portable drill. And this portable drill does a good job of kind of demonstrating braking, because when I use the drill, I pull it, right, and the current comes out of here, goes to the motor, turns the motor, and it spins. And then I let it off. Did you see how quickly it stopped? Because I didn't just disconnect the battery. I mean, if I just disconnected the battery, it would look like this. And it would just slow down because of friction. So I'll say it again, this is slowing down because of friction. But if when I release the trigger, it makes a connection so that this spinning generates an eddy current which goes back to the motor, it recharges that. Now, in this case, the point is not to recharge the battery. The point here is to make it as a brake so that when I'm driving a screw, I can go and stop right at the right spot. And so it's going to take advantage of those. Well, like I said, this discussion is quite interesting, and the math is over the top. So good news here, we won't do any math. We'll just say, all right, let's talk about the idea, and then move on to what could be very useful. And so that's the next section. And so section 5 says, all right, how is most of the electricity created? And it is actually moving magnets, as I was talking about yesterday. And I'll hook it up again. Here's the big magnet. Let me get it near this coil. But as you can see, I've got this magnet that is so strong, most of the field is here, but it does loop around a little bit here. And if I bring it near, you'll see it generates the current. If I pull it away, it generates it. But instead of changing the field by actually changing the position of the magnet, why don't I change the flux by changing the orientation of it? And so the flux goes in, out, in, out, in, out. And so it's constantly changing the flux. And the flux then would create a voltage. Now, here, though, is why I was saying last time, there's this natural process that's going to create an AC EMF. And so it's going to alternate on me. Now, better picture than this is this one here, as we started to see yesterday. And I'll put your author's picture up here. Actually, I think your author had it this orientation. Let me take a look at his picture here. Oh, by the way, some of you might find this interesting. Back to our eddy currents. This is another nice process on the fine balances. You put a little magnet near it, a little electromagnetic braking. And that way, when you go to weigh something, it doesn't sit there and teeter forever. So if there's any movement, it comes to a stop. But if there's balance, then there's no movement, the magnet has no effect. So the balance still works just as well, but has a little magnetic braking in it. And so the balance scales are real nice with that. Separating recyclable materials also is really nice with that. Looking for other metal pieces like mines are really nice for that. Anyways, I'll let you read more of those details. I want to get down here to kind of an important piece of technology, and this is how do we make the electricity that we constantly plug our lights and our phones and our TVs and computers into. They use a very simple idea here of a generator. And so here we have a set of magnets, so North Pole and South Pole. And so that's what I have here. I have a North Pole and I have a South Pole. And I have a rectangular loop. And if I spin this loop, this isn't really designed well to be orientated this way, but I want to match your author. But if I spin it, I'll have a change in flux. And so your author says, all right, let's do the math on this one. Let's calculate what the EMF is on here. And so, all right, let's give this a little mathematical try here. I keep setting that thing somewhere. All right, I'll go to blue. Oh, there it is. All right, so in our electric generator, if I say the EMF is, and I've got the number of turns, and then I've got the derivative of the flux. So that's the general principle. Then, I got it, Ron. All right, then, if you say, okay, what is the flux going through a rectangle? Well, I still have this one out from yesterday. Okay, so here's my little rectangle. Okay, and so you can imagine this rectangle spinning. Okay, so the flux would be the strength of the field, which is coming from these magnets, then time this area, and then cosine of the angle between them, the orientation. And that's the thing that's changing here. So I would put B for the size of the field coming from the magnet. I'll put A for the area, that would be this height and this width, okay? And then I will have cosine of theta. Oh, and I forgot the derivative. Derivative of the flux. And so like we did with the motion EMF, where we take a derivative, let's look for things that don't change. And for this one, we're going to say the field is a constant, and the area really doesn't change. The orientation changes, but the area doesn't change. The motion EMF, that was what changed, was the area. But I'll say here's a B, here's an A, and then I would have a derivative of a cosine theta. And here I'm going to have to say, okay, let's go back quite a few chapters, actually, to Physics 110. And do you remember that equation on rotational motion? Remember our rotational kinematics? It was kind of a repeat of our translational kinematics. One of the equations we had was to say, well, I'll start with translational. And put its matching equation based on rotation. And if you just say, let's have something spinning at a constant speed, so it just spins around at the same constant speed. In other words, it would have no alpha, no angular acceleration. So this term would go away. And just for the sake of simplicity, if you say it's spinning, let's just say it starts at angle 0. So we'll start it at angle 0 and start it spinning. So we actually have a very simple equation for the angle based on time. It's just omega times t. Just like you would have distance equals velocity multiplied by time. Here we have angle would equal angular velocity multiplied by time. See, I want to take advantage of that and put that right here. And so this is saying the EMF is equal to NBA, and now I'll have the derivative with respect to time of cosine omega naught t. Do you know the derivative of cosine? Sine? I guess it's negative sign technically, I guess. And I've kind of ignored the negative. Maybe I should put it back in, but if I put the negative here and then I take derivative of cosine, I get negative sine omega t. But the big piece is the chain rule. So after you take the derivative of cosine, you have to take the derivative of the inside piece. And so there's an omega. And you could say the two negatives cancel out, or we could just ignore them altogether. We were talking about magnitude anyways, just to kind of get a general pattern. But here's what I'm trying to get at. That if I go ahead and do some of the calculus for you, you won't have to, all right? And so we've got a nice little formula that says how much voltage would you get from a configuration like this. This is called a generator. And you can now see the sine function is the sinusoidal piece of it. Right? And so this is its magnitude. And so what you're saying here is if you have a rectangular wire that's spinning in a magnetic field, it will produce an EMF that apparently, as we read the math, looks like this. It looks like a sine function with this amplitude. And so if I plot the EMF as a function of time, it would go up and then down, and then up and then down, and then up and then down. And this was our discussion on our circuits, I guess chapter 21, or maybe it was 20, at the end of 20, where we said, hey, sometimes instead of having just batteries and we have a DC current, we have an AC current. I even mentioned, you'll see later on, and here we are later on, that the reason our wall plugs are AC, a couple reasons, but a big one is they're just so simple to make. This is just natural. A moving magnet, or I should say a spinning magnet, makes this AC voltage. Now, how tall do you make it? In other words, its amplitude, you can see its maximum depends on 4 factors. And not a surprise on all these 4 factors. I mean, the first one is the number of turns. And that makes sense because, like I was saying earlier, you get a voltage for every loop. So if you wanted to double it, you just make another loop and another loop and another loop. So you can make whatever voltage you want by just making more and more loops. And of course, the other 2 factors, the B and the A, kind of go together because those are the flux itself, right? The flux depends on both of those. And so you can see that if B is bigger, you'll get a bigger field, a bigger EMF. If A is bigger, you'd get a bigger EMF. So again, the fact that the magnetic field strength, and so how big these magnets are, or how strong the magnets are, I should say, or how big this area is, kind of totally makes sense. The last piece of it, though, I want to really focus on is the angular speed. That is the fundamental principle for this chapter, and it comes all the way back here to Faraday's law. Faraday's law says the EMF is based on the rate of change. So something that's spinning faster has a bigger rate of change than something that's spinning slower. So it makes sense that how fast it's spinning should come into play. And especially as we get into some other sections in our electronics here after the break, I want to keep that in mind, that remember what Faraday's law is really saying. It says the EMF is related to or proportional or equal to the rate of change. So it's not just the flux, it's the rate of change. So the B and the A is the amount of flux, but the omega is the rate of change. And so, again, you want to get a lot of voltage out of something, a generator, spin it fast. Because, again, it's the rate at which it's changing that's important here. All right, well, let me try an example here then of a generator problem. Let me do number 28, now that we mentioned it here. And so, jumping to the end of the chapter, and jumping down here to number 28, it says here, calculate the peak voltage of a generator that rotates its 200 turn, 0.1 meter diameter coil at 3,600 RPMs in a 0.8 Tesla field. So they give us all four factors. So again, the hard part is kind of understanding what's going on and then doing the math. Now that we did it together, I could say that this N, B, A, omega naught is the EMF maximum, right? It's the maximum voltage. So a wall plug, the voltage keeps changing, goes up and down, goes positive, negative. Again, that's why we call it AC, alternating. And this one is just simply asking us to say, okay, plug it in and see what you get. By the way, I should pause at 3,600 RPMs because that is the speed that we, being the United States, Canada, Mexico, North America, have agreed to. And so our grids are all connected together and all our generators are spinning at 3,600 RPMs. It comes out to be 60 times a second because, right, 60 seconds times 60 times a second is 3,600. And so if anybody asks, you could say, oh yeah, the wall plug right there is AC. And it's AC because the way generators are made, they're rotating magnets or rotating coil in a magnet. You could rotate either of them, you know, as long as there's a rotation. Usually the coils are lighter than the magnet, so you usually spin the coils and not the magnets. But there's kind of nice about spinning heavy things too. They're kind of stable. But the idea is the same. And then all these places were generating electricity. I'll just pick on Hoover Dam here. And so we've got water coming out of Hoover Dam and it's spinning around the turbine and the engineers there keep it going at 3,600 RPMs. And if somebody turns on a bunch of lights or an air conditioner, like, ooh, let more water push it through because we're trying to keep it at 3,600 RPMs. And so the AC goes up and down 60 times a second. All right, but if I put in the numbers that were given here, looks like I've got 200 turns here. Okay, the strength of the field was the 0.8 Tesla. The only thing that might take a little bit of work is the area. Okay, well, they seem to imply that it has a diameter, so I think they're calling it a round spinning coil instead of what I was showing you was kind of rectangular, so they're spinning something like this. The other thing you ought to be careful for is make sure you cut diameter in half to get radius. So the area would be pi and 0. So it says 0.1 diameter. So let me go 0.5 meters and square it. And another thing to be careful is the units here. They say 3,600 RPMs. Well, let me just put it in as 3,600, revolutions per minute for a second. And maybe I'll give myself some space over here so you can see the units. But those are not your base units. And so you want this to come out to be voltage, in volts, I mean, an EMF, a potential. So we really want radians per second here. So we've got some unit conversion here. All right, so I'm going to put the 200, and there's no units there, that's just a number. I'm going to put a 0.8, and I'll put the unit over here, Newton per coulomb per meter per second. So there's the Tesla. All right, so here's the area, pi times 0.05 squared, and so that would be meters squared. And then I will put 3,600, but remember that's a revolution per minute. All right, so again, we got to go back to some previous chapters, in this case all the way back to Physics 110, all the way back to our kinematics. Hopefully we remember that there is 2 pi radians per revolution. So that's going to get rid of revolutions and convert it into radians. Hopefully we also remember that we want to get rid of minutes and turn it into seconds. And so we'll put minutes up in the top and seconds in the bottom, and to make it equal to 1, remember we can't just throw a number in there and multiply by anything we want. Got to be equal to 1. This is our unit conversion. And so that would then get minutes to cancel off. And now, if you look at your units, you will see this seconds over here cancels with that second. One of these meters cancels with one of those meters. Then you'll have newtons times a meter, that's a joule. A joule over a coulomb then is the definition of a volt. So I got volt. Now you might say technically I have volt times radian, but as you guys heard me say in 110, radian is not a real unit. Right? It's a clarification. The Greeks came up with the idea of an angle by taking the arc length and dividing it by its radius. And so length over length is no units. We just call them radians so that we don't confuse them with degrees. And so if it makes more sense to call them radians, do that. But if it doesn't, get rid of it. And so I say in this case it doesn't, so get rid of it. All right, so now I get my voltage. Okay, so finally now I can get to my calculator. All right, so this is 200 times 0.8 times pi times 0.05 squared times 3,600 times a 2 pi divided by 60. And so this is a peak of 474 volts. Which I was trying to see if there was anything significant about that number, and I can't think of anything here. I thought maybe it was our 440 volts that we use in factories and stuff, but it doesn't seem to be that either. So not sure what the significance of that particular one is. Anyways, this would be a good break time, so let's take a break. But again, hopefully now you're seeing one of the biggest reasons of Faraday's law, and that is generating electricity so we can run the world that we run in and plug. All right, take a break and we'll come back at 11:45 and continue on more on this chapter. Hey, okay, welcome back, and we'll get started again here from our break. Like I said, big chapter, lots to cover, and so let's see how far we get. But I noticed right before the break, we kind of ended with our generators, and I was a little bit past break time, so I went with it. But during the break, I thought, I might as well show this. I know time is important here, but I was showing you the generators, and so here's kind of a fun one to show. Here is the hand crank. And of course, you can't really see the magnets, but I like this model because it was clear. You can kind of see the gears, and the gears move inside of here. There is a spinning magnet, and so the moving magnet makes the electricity, and so you get the light because of the spinning part of it. I also like it because if you remember, this chapter started with the symmetry of that butterfly, and I was commenting last lecture how I go, that was kind of weird. Why'd they have a butterfly? And they like that, and I'll just repeat, they have the butterfly because the butterfly shows a lot of symmetry, and so they were trying to say physics has a lot of symmetry, and so if magnetism came from electric fields, then the reverse ought to be true, and that's what we're seeing now. We're seeing how magnetism now makes electric fields here, and that's what. This is kind of fun. This one is really the same model, except, this one right here has a light bulb plugged into it. So when I crank it, the electricity goes to the light bulb and the light bulb goes on. Okay, but this one doesn't have a light bulb. It just has some wires here. All right, so when I crank it, I got my little generator going. However, I don't know if you recall this, but we talked a little bit about electric motors, and you might recall that I used this same crazy configuration when we talked about how an electric motor works. And now I'm using it for a generator. There again is that symmetry. And so if we put electricity into this, it makes motion. That's a motor. That's what we did in the last chapter. This chapter, we're doing the reverse. We're taking some motion and then making the electricity out of it. And so that's the symmetry that they're talking about. Electric fields can make magnetic fields, but magnetic fields can make electric fields. And they go back and forth. And the reason I find that quite interesting here is because I have two of these. And now I don't know what to call them. Do I call them motors? I call them generators. Because if I put electricity into it, it spins and it's a motor. On the other hand, if I spin it with my hand, I make electricity come out of it. So it's both a motor and a generator. It all depends on what I'm trying to do. And you can see that in kind of a neat way here. Let me give myself a little bit of room here on this front table, because I'll take this one and I'll call it the generator. So I'll kind of crank it here. But I'll take this one and I will then send the electricity to that one. So this will be the generator, and that one will be the motor. Of course, the reverse is true. Although I'm kind of missing a handle here, but I can spin this one. This one becomes the generator, and that one becomes the motor. All right. So that was one thing on break that I go, before the break I go, it's time for a break. We need a little rest there. But I wanted to show that to you, and I go, well, I'll take a little time to do it. All right, let me jump right back in here. Let me go to section 7 of this chapter. So section 7 is on transformers. Another very important piece of our modern technology. And so like I said, we got the basic physics, and the big thing was these generators. And another big thing are these transformers. And so I like the way your author starts this. He says, look, if you have a power plant, which is making the electricity, they have these generators in there. And so somehow they're making motion. And so somehow this is spinning. Like I said, this could be, I picked on Hoover Dam, this could be water flowing through a dam that spins this, but this could also be out in the Palm Springs area if you've ever been and see the wind farms out there, and you got the wind blowing and the wind turns the windmill. You just need something to turn it. A lot of science museums, they're fun to go to because they often have like a bicycle that you can pedal, and the chain turns a little generator, so you get to turn on little lights and you get to make electricity from yourself as you are pedaling the bike. So you just need something that spins it, whether it's the wind, whether it's water, or what is done most of the time is we often then use some kind of fossil fuel. California, it's all natural gas, and so we burn the natural gas. We use that heat to boil water. The water boils, that makes steam, and so the steam goes shooting down the pipes under pressure, so it's like a wind, and then the wind turns the turbine. So all of our electricity really then is something that turns the magnet to make it move, whether it be boiling water or water flowing in a river, or wind blowing through, or even nuclear energy making heat and then boiling the water, making the steam, which is equivalent to the wind blowing. And so that's how we make it. But how we deliver it is what I want to talk about next. Is we then generate it maybe at 12,000 volts, but we transmit it, especially great distances, at a higher voltage, and this is 400,000 volts, When we get into the city, we step it down to about 13,000 volts. And I should say there's a lot of variations depending on where you are in the city, how big the city is. But these are just some random numbers of maybe a small town. And then you have these high power lines. So as you walk around town and you're walking around, you see the main streets and you see the power lines real high. Those are probably your 13,000, your 16,000, your 32,000 volts. But of course, ultimately then it's stepped down again in a little pole usually in your backyard. There's a telephone pole, and up at the top there's those high wires that are at 13,000. Then they feed into this thing called a transformer and lower it to 240, and then that's what enters your house. And so what ultimately comes into your house is kind of a balance between safety and efficiency of what the voltage is. And so it's 240 by the time it enters your house. But all of these changes in voltage, going up, going down again, involve transformers. So what is a transformer? Well, as I said, the best thing I can say is a transformer is a short word for, in electrical engineering, what we call transforming the voltage. We can step it up or we can step it down. That's the names we like to use. But how it works is based upon Faraday's law. So it's a perfect piece for this chapter, and maybe this is a good picture of how I might design it. I'll call this the primary and then the secondary. See, the same terminology we have been using with Faraday's law here. What you would do is you would make some kind of magnetic flux and then feed that flux into the secondary, and that would be generating its own voltage. And so I'll put this equation here on the board again. The EMF is equal to, again, the number of turns times the change in the flux. Let me write this equation twice. And to keep track of the two, let me do a little notational change. Let me call this N sub P, the number of turns in the primary, the flux that's in the primary. For this one, let me call it the secondary. So this would be the EMF of the secondary, the EMF of the primary. Now your author changes his notation from EMF to voltage, and I'm not sure why he does. I hope that's not too confusing, but right here he calls it voltage of secondary and primary. So I'll follow his suit, but I think that's kind of confusing, but I'll go ahead and do it. So this is the voltage of the primary, and this is the voltage of the secondary. But here's kind of the thinking. The thinking here is, what if you did this? What if you took a wire and made it in a coil? Now, sadly, this might be a little hard to see. One of these is falling apart. It might be a little easier to see, but there's actually wires under this black electrical tape. And this one says it's wrapped around 55 times. And this one here says it's wrapped around 110 times. Okay, so I'm going to take this device, which by the way is also a transformer, so we'll talk about it once we figure out how these things work. But it's plugged into that wall. And so it's a pretty high voltage. And so to make it safe, I'm going to transform it down to a safe voltage. So how this works is exactly what this is. This is a transformer. See, what I'm going to do is I'm going to take this and call this the primary side. This is where the voltage is being fed in here. And so I'm going to hook up these two wires, although I'm not going to hook it up quite yet. So I'm going to take this voltage here and connect it right here. And so what will happen is current will begin to go through this primary. He calls it number of turns in the primary. And that's going to make some flux. And then the flux is directed into a second coil. And we use these little magnetic bars for that. And so in my setup, you can kind of see it here. this is my secondary. And so what I'm going to do is once I hook it up and have current going through here, and remember it's plugged into the wall, so like we said before the break, this is AC. So it goes one way then the other way. So there's a constantly changing of the flux. And then I'm going to direct that flux with these metal bars into this secondary. And because of Faraday's law, there's going to be a change in flux here, and that's going to make a voltage. Now, there's no point in talking about the direction because this keeps changing, you know, up, down, up, down, up, down. So this is going to be opposite, down, up, down, up, down, up, down, up. But so it's still going to be an AC. So the good news here is I won't get into Lenz's law about what direction it is. I'll just say this was constantly changing. So this one is constantly changing. But I would say is how much voltage then is produced in the secondary could be more or less voltage. It doesn't have to be the same. Hence, it transforms. Watch, you can see it in the math right here. If you take the number of turns in the primary and move it over here, you're going to have the flux that changes in the primary. Now, if you do the same game here, you will have the amount of flux changing in the secondary. And in a perfect world, and of course we'll say there is no such thing as a perfect world, but in a perfect world, if you could direct all the flux from the primary through those metal bars and into the secondary, those two changes in flux would be the same. The flux that is generated by the primary gets fed into the secondary. That's our Faraday's law. And that's why there is a voltage produced on the secondary. So if I, like I said, in an ideal world, set those equal to each other, then I would have an equation that looked like this. The voltage in the primary over the number of turns in the primary must equal the voltage in the secondary over the number of turns in the secondary. And if I rearrange this equation, you can see we have a simple and wonderful opportunity to change the voltage in the secondary based upon the primary, based upon how many turns you have. And it kind of makes sense. If you have more turns in the secondary, you get more voltage. Then it's a step up. And so more turns in the secondary, of course, would produce more voltage. And that's what we call a step-up transformer. But on the other hand, if you have less turns in the secondary, well, you're going to get less voltage. So I will illustrate it here by saying, all right, let me take a voltmeter. Let me plug in the voltmeter to my primary. And I will just say right now, this primary is giving me 7 volts. If you want to see me plug it in here, you'll see it drop a little bit, but it's still close to 7. But see, now this is making some flux, and the flux is going from the primary into the secondary, and that should be producing some voltage here. And sure enough, this voltmeter says 2.4. Now, it's not really the same amount of flux because I moved this metal bar. So to make it a little better, let me put this metal bar back on here. Let me kind of hold it tight so maybe I can get as much flux through there. And so I'm putting in 7, and what's coming out is 7. Actually, it's a little over 7 and a little under 7. So apparently I'm not getting all the flux, but what I did do is I put 110 turns here and 110 here. So these have the same number of turns. And according to this math, if they have the same number of turns, and this ratio is 1, and so what I get in the secondary should be the same in the primary. There should be no increase or no decrease. And obviously, if I don't get all the flux in there, there is a loss. And so something like this, there's a huge loss. Something like this, there's a little bit of loss. So I would say here, most of the flux is getting through. And so if I wanted to then change this and make it a step-up transformer, let me remove the 110 and replace it with 220. So now this ratio in front, 220 over 110, this is a factor of 2. This would be then doubling the voltage of my primary. And so if I plug it in, I should I lied. I grabbed the wrong one. Sorry. This is 880. All right, so let me be a little careful with the voltage, because, see, this is 7. So 880 would be 8 times. So this should be about 56 volts, minus the imperfections of my flux. All right. But definitely a step up. Yeah, see, I get a little lightning signal. Be careful. You're above 30 volts. All right, so I'll be careful. But there it is, 54. And so that's a huge step up. And more than I intended to show you on the first step. But maybe that's just as well. This is the one I meant to show you. Here's the 220. The 8's are kind of worn off a little bit, so the 8's kind of look like a 2. But here's the 220. And so this should double it. So 7 doubled should be about 14. And so this should be roughly a 14. And so sure enough, it is. And maybe I'll show you one more, and I think you get the idea. How about a step down transformer? Here's 55 turns. So there's half as many turns here as in there. So this should step down the voltage. And it should be about a step down of 1/2. And so hopefully I'll be around 3.5 volts or something. So here's 7, here's roughly 3.5, 3.2. And so it steps it down. Which now maybe it makes more sense why then I took this and I plugged it into the wall, which is a really high voltage of 120, and I used this fancy thing called a transformer and stepped it down to something that was a little more safer to handle here. And so I've got 7 volts here, and so I'm using a step down transformer to then feed that into what we call the digestible transformer, so that students can learn what's going on inside and see how it applies to Faraday's law. And so there's our step down. Now, in case you're wondering, I should say, even though we're stepping the voltage up, there's not a free lunch here in the sense that you get more energy out of it. So I will say that the power coming in from the primary still equals what then is being delivered on the other side. In a perfect world, I would say it's even a little bit of less, because there's always some lostness. And so if we go back to kind of our city delivering system of electricity, we might say, hey, we generated it at 12,000 volts, but then we stepped it up to 400,000 volts. So we got more voltage. However, we got less current, because the current in the primary times the voltage in the primary must equal the current in the secondary times the voltage in the secondary. There's not an extra energy source. So if you step the voltage up, the current has to go down by the same proportion in order for the energy still to be the same, and conservation of energy. I like to write it this way, that if you come back and remember here, maybe I'll write it as Vs over Vp, and on this side Vp over Vs. then you can come back and look at here, Vs over Vp would be Ns over Np. And so if you solve for current in the secondary, it's going to be equal to the current in the primary divided by this ratio of the number of turns. But notice the primary is on top, so the reverse effect for the current compared to the voltage. So if the voltage is stepped up, the current is stepped down. Or the other way around. And that's really kind of the whole purpose here, is the whole purpose of this stepping up the voltages is so that you could have a lot of voltage but very little current. Because these wires might be spreading out from Hoover Dam over to Santa Barbara. So you got 300 miles of wire there, and the loss of energy, remember, is I squared R. And so you got these metal wires that are 300 miles long. You're going to lose some energy as they go from the generating station to where you're trying to deliver it. And you want to make that as small as possible. And the way to do that is make the current as small as possible. But the problem is you want current when it gets to the city. So how do you get all this energy to the city without delivering a lot of current? Well, you step up the transformer. You do a step up. So what you are essentially doing here is delivering voltage, then you step it down to deliver current. So by the time it gets to the home, you didn't have to deliver the current the whole 300 miles. You just delivered the energy the 300 miles. And so that's another huge advantage of these ACs and these transformers. They're very easy to step up and step down and to change their voltage with Faraday's law. It's just a bunch of wires and magnetic material, and you can get them higher or lower. So it's a very simple and clever design. Makes it efficient, and then makes it allow us to make our voltages higher or lower. In fact, these days they're very, very common. If you ever kind of wondered what's in that little white cube, if you have an iPhone or an iPad, you know, it's got a little plug and you plug it in. It's got one of these. It's got a transformer because you're charging your phone. You're only using 5 volts to charge your phone, but you're plugging it into the wall, which is 120 volts. How do we get this lower voltage? Well, we run it through a little transformer first. It does something else too, because it changes it from AC to DC, so there's another step in there too. But the big one is just to lower it down to a voltage. You probably see it on your laptop. I bet all of you have a laptop computer, and when you plug it into charge, don't you plug in the wall, and then about halfway down the cord there's a little box, and then the cord goes the rest of the way? That little box, now it's a bigger box than your iPhone, but it has a transformer in there to step it down, and then it has some other electronics to change it from AC to DC. And so that's the purpose of those things. And so we constantly convert from our AC to our DC. All right, well, maybe this would be a good chance to do another example. Let's look at number 44. I've got 2 here, but we might run out of time, but I'll put it here, number 44 and 46, and see what we can get accomplished here. So 44 says 1052, 44 into this category of transformers. It says a plug-in transformer like the one shown in the picture supplies 9 volts to a video game system. How many turns are in the secondary coil if the input is there's 120 volts and the primary has 400? All right. Well, again, most of this chapter, even though it's a pretty long chapter and a pretty complicated chapter, I must say the problems are pretty straightforward, because the hard part is kind of working out these equations. Another hard part might be kind of recognizing, well, which equation do I use at which time? You guys saw me do that for the motion EMF before the break. I said, look, the hard part was to recognize that that problem was a motion EMF. It wasn't hard to calculate it. It just had B, L, and V. And I would say the same thing here is you just have to recognize that this is a transformer problem, because once you do that, they give you 3 of the 4, and then you just plug it in and solve. So they said what's coming out of it is 9 volts. What's going in is 120. And I forget which one they gave us here. So coming out of the video game is 9 volts. How many turns are in the secondary? So we're looking for the secondary. Given that the input, so the primary, is 120, and that there's 400 in the primary. So the primary has 400, and we're looking for the number here. And you can see that it's a step down quite a bit. If this was 12, this would be dropping it by a factor of 10, which of course would make that a 40. And it's even less than that. It's by 2/3. So that's got to be a 30. Let's see what the math gives me. So my guess is we're looking at 30 turns. 3/4 of 40. And so I'll take a 9 and multiply it by 400 and divide it by 120. And sure enough, there's 30 turns in the secondary. So a step down transformer. And I think 46 is a little discussion about the current. 46 says a cassette recorder uses a plug-in transformer to convert from 120 down to 12 volts with a maximum output current of 200. What is the input? All right, well, let me start with the given information, because the output of this, and so if I take the voltage of the secondary, it's equal to the number of turns in the secondary over the number of turns in the primary times the voltage of the primary. They don't directly tell me the number of turns in secondary or primary, but they do tell me the voltages. And they gave me a nice easy number to work with. Because if I divide both sides by 12, I get a 10. So 1/10 is the number of turns in the secondary compared to the number of turns in the primary. So again, it's a step down transformer. And then not knowing the number of turns really isn't important. It's the ratio of the number of turns that's important. Because this one says, what is the current in the input? So let me take this one right here. So the number of, or the current in the input, the primary, is equal to the current in the secondary. And then here's that ratio, the number of turns in the primary over the number in the secondary. And so it's the reciprocal of this. So I'm going to put a 10. In other words, the current is stepped up by a factor of 10 when the voltage is stepped down by a factor of 10. Right? So the energy stays the same. All right, now I forget which one they gave us. They gave us the output or input, 46. What the question is, what is the, let's see, the maximum output is 200. So the output. So this is 200 milliamps. And I'm looking for the current in the primary, so I'll bring the factor of 10 over here and say it's 20 milliamps. So we have a little bit of voltage going in, a little bit of current going in together with a lot of voltage going in. So big voltage, small current. What comes out of the transformer is the opposite, a lot of current and a little bit of voltage. So the energy is the same, but we just transformed it from high voltage down to low voltage. Or you might say low current to high current. Okay. Then it says, what is the power of the input, and is the amount of power reasonable for this small appliance? Okay, well, if I'm doing the power on the input, and so I'll say power primary, this would be current primary times voltage primary. And as we just solved, it is 20, the primary is 20, the secondary is 200, but the primary is 20 milliamps for the amount of current. The voltage was the 120 volts. And so putting that together, let's see, 2 and a 12 makes a 24, 2400 times 10 to the minus 3, and an amp times a volt is a watt. Why don't I just take the 10 to the minus 3, put it right there, and so this is 2.4 watts. And yes, that would be the appropriate number for a small appliance here. Do you guys even know what a cassette recorder is? Oh, yeah, okay, you do. They're not that old, okay. All right. You have one?
No, I just Urban Outfitters.
Okay. So, that could probably be an updated question. But anyways, an iPhone being charged here or something. Anyways, hopefully that will help. Now, let's do two more big things, kind of challenging things here. But again, hopefully you'll see it's just Faraday's law and a lot of math. And so we might have to shortchange you on the math, but it looks a lot like we did with the capacitor. In fact, that's where I want to start. I want to start by jogging your memory back to when we charged up a capacitor versus now we're going to get a new thing. We're going to call it an inductor. And it doesn't have charge, so we'll say we're going to energize our inductor. But this category, so sections 9 and 10, are what your author refers to as a mutual and a self-induction. And he's got a nice picture with mutual induction. And so let me go back. We must have been on about page 30. Oh, perfect. All right. And he says this. He says, look, what if you were to have one coil that has current in it and then nearby is another one? Isn't there then a mutual effect? This one affects the other. In fact, I would say that your author's already done mutual induction. What this transformer is a mutual induction. This transformer is saying, look, you've got current going into this primary, that gets fed into something else, and so there's a certain amount of voltage in that secondary. And so I'm not going to spend much time here because I think really the transformer covers it really well. It is kind of nice to see it in a kind of a different venue, if you will. So I like this crazy coil. Let's call this big old coil here my primary, because I can plug it in. And in this case, I'll plug it in here. And so if I turn it on and crank up the voltage, I would say right now there's current going through this primary. And remember, I'm plugged into the wall. So the important thing from the wall is to remember it's AC. So as the current goes around, we got flux this way and then that way, and then this way and then that way, and then this way and then that way. And so right here, even though you can't see it with your eyes, I'm trying to give you this visual effect that there would be some flux. So I don't know if the room's dark enough. Can you see the light go on? And I would call this then a mutual inductance. I would call this a Faraday's law, because what's happening here is right here, there's currents going through my primary. And it's constantly changing. And so the whole point of this chapter is to say anytime there's a change in a flux, there is an EMF. And so right here, there is an EMF. And so if I put something right here, and so this is kind of difficult to see because we covered it in wax, but we wrapped a wire around here 200 times. And then put a little light bulb on here, so that when you put it there, the light bulb goes off. When you pull it away, there's no more light bulb. And in fact, well, never mind. Let me show you some other ones here. To kind of help balance it, I'll put a little metal core here. But here's kind of a fun one to do, is what happens if I put the ring there? What happens if I turn it off? What happens if I turn it on? And see, again, I would call this a mutual inductance because it goes from one into the other. And in this case, it makes the flux go into here. And this is kind of like the braking one we did before the break, because this is going to set up a current, and the current's going to be opposite. And so at one given moment, this side could be thought of as a little north pole, and then the current that's induced in here could be thought of as a north pole, and they repel each other. Now, a moment later, they switch, and so this becomes a south pole. But remember, this is opposite, so it becomes a south pole. And so it's constantly repelling itself, and it's kind of hovering. In fact, you can even kind of hear it kind of ring, click, click, click. That is the fact that it's turning on and off. Remember the 60 times a second, the 3,600 RPMs? This goes north pole, south pole, south pole, north pole, south pole. And it constantly repels itself, but there is a moment that it kind of drops. And so it kind of has that ringing effect. In fact, it's kind of best to see it with this one. This is that same kind of ring, but we cut it with a bandsaw. And so this one can't get any current to go through it. It's been cut. So the secondary here can't have any current. And if it can't have any current, this one does not become a magnet. Sorry, this one does not become a magnet. This one does become a magnet. So this one, because it's a closed loop, will get current in it and it will repel each other. But this one, because it's cut, doesn't get any current. And it's exactly the same thing I was trying to show you between these two. That this would get some eddy currents. This one would get almost no eddy currents. There were some little ones because I didn't cut the lines that close together. But I cut them so that the current wouldn't make the little circles. And there wouldn't be that repulsion, and we wouldn't have that braking effect here. And so that is our little induction. And there's some other neat things too, but I better move on here and say, all right, let me put this out of the way here and say, all right, if that's mutual inductance, we kind of already covered it with the transformers. So what is self-inductance? That's a little harder. And self-inductance, as the name implies, is an induction on itself. We keep talking about the flux from the primary to the secondary, but isn't the flux in the primary changing within itself? In other words, watch this circuit. What if I did this? I took a battery and I connected it to a coil. So I'm going to give you a new picture here. Okay, this is what we're going to call an inductor. And we're going to talk about the inductance of this inductor. Now, just to make the discussion a little simpler, I'll put a resistor here. But also, maybe to make it a little more understandable, we probably should go back to the battery, the capacitor, and the resistor. So here's the capacitor, here's the resistor, here's the battery. We called this an RC circuit. And we said something to this effect, that if you were looking on the voltage or the charge on the capacitor as a function of time, we said because of Kirchhoff's law, which is conservation of energy, if you add up around the loop, you're going to get the total energy equal to zero. That is, if you take the voltage from your battery, subtract the voltage from the capacitor, subtract the voltage from the resistor, you would complete a loop that would be equal to 0. Or put another way, the total voltage of the capacitor and the resistor would equal the battery. And so we said something like this. We said, when you first connect it, charges start flowing. But at first, there's no charges on here, so there's no voltage here. So the voltage on the resistor would be the 6 volts, if this was equal to a 6, and the voltage on here would be 0. So I'll put voltage on the capacitor here. But if I put a graph here, which would be the voltage on the resistor, which would be the same as the current, we would say the current would start high and taper off. And the same thing would be true in reverse for the capacitor, because the capacitor would start with no charge and then it would build up charge until it got fully charged. And so as the amount of charge, or I should say the amount of voltage, increases on the capacitor, the amount on the resistor decreases, because these two add up to a total of 6 all the time. So at first it's 6 and 0. A little bit later it's 5 and 1. A little bit later it's 4 and 2. A little bit later it's 3 and 3. A little bit later it's 2 and 4. And then 1 and 5. And now finally 0 and 6. And so this gets a full 6 volts by the time this drops down to 0. And we had that exponential decay. And so this looked like V equals V naught 1 minus e to the minus t RC, right? That time constant. So if all that kind of rings a bell back to you, I'm going to say the same thing happens with an inductor. But an inductor gets its electric field a little bit differently. Remember I said at the beginning of this chapter, there are 2 ways to make an electric field. One of them is with charges. And so I would say that in the capacitor, you're building up positive charges here, and the other side is having negative charges. And you would then say, inside here, there is an electric field. And this electric field is the whole reason it starts opposing more current from charging. This battery is trying to send it out to the capacitor, but see, the capacitor is building up its own electric field, which opposes more electrons from coming to it. And that capacitor, like I said, is having an opposition to the current based upon the electric field. And the electric field comes from charges. Could we have an electric field in the inductor? Where an inductor really is nothing more than this, really, literally. It is nothing more than a wire in a loop. And so a wire in a loop, how could this possibly make an electric field? Well, again, that's what this chapter is about. It's a little harder and more advanced chapter. But yes, you can get an electric field here, because if there's a change in flux, and it could actually come from itself. That is, when you hook up the wires, the current starts building up. And as the current starts building up, it's going to be creating a flux. And if the flux creates in itself, that magnetic flux is then going to create an electric field. And so I would argue that there is a very similar pattern between these two. That here you're getting an electric field, what I would call the new, or the original method of getting the electric field, by just charges. But here I'm going to say that there is going to be an electric field. Sometimes we call this a back EMF. And that's coming because you're trying to hook this up and you're trying to make current go this way. You also need to remember that Faraday's law only produces an EMF when there's a change. So this would only occur when you hooked it up. But again, that's what happens here. You only begin to build up charges as you first hooked it up. Once it kind of settles in after a couple of microseconds, everything's just kind of stopped flowing. Of course, you constantly have a electric field. This one's only going to make electric field when the current is changing. And my point is, the reason we call it a self-inductance is because it's the current that goes through myself that then makes a magnetic field. That magnetic field is changing, so that then makes an electric field which opposes the current. And so these two have a lot of similarities, but you also might say they're kind of the reverse in each other. In other words, here's kind of what I would expect. If I were to make a plot of the current versus the time, you might even say the current is the same as the voltage on the resistor. And I suppose I could compare this to the voltage on the inductor. And so let me take this as an opportunity to say, here's our new symbol. We're going to call this an L. And so this is going to be referred to as an LR circuit. And so I have an inductor and a resistor. And what I'm trying to do is get you to see the comparison, especially since we've already done capacitors. And especially since this involved a little bit of calculus. Why don't we skip the calculus? Why don't we just say the calculus is going to come out the same as this one as we did that one? And so I can come over here and say, all right, if I were to make a chart of the voltage on the resistor and the voltage on the inductor, and I guess I never did make a chart for the voltage on the resistor and the voltage on the capacitor, but I was saying the capacitor would build up and the resistor would drop down. But the total was always 6. And I'm going to say the same thing here. When you first hook this up, what you're trying to do is rush current through here. Remember Faraday's law? The amount of voltage, in this case the voltage on itself, the back EMF, is related to the rate of change. And so I would say right at the beginning, the rate of change is the strongest. And so that's when you're going to get 6 volts on your inductor. You're not going to get any current. You're trying to change the current. Remember Faraday's law, you get a voltage not because there's a current, not because there's a magnetic field, but because there's a changing one. And so at first, you get this huge voltage on the inductor. And so it would be 6 on the inductor, but 0 on the resistor. Now, I'll also point out that this inductor and a resistor are in series. So whatever current I say is in the resistor, it's also in the inductor, so keep that in mind. So maybe I'll put current in the resistor, but this is also current in the inductor, because that's my ultimate goal here, is to say, what is going to be the current in this inductor? And my comparison will be the current in the inductor will behave a lot like the charge on the capacitor. It'll start off at 0 and build up. Of course, there will start to become current through here. And so this number is going to go up, meaning this number has to go down. Because again, Kirchhoff's loop, they have to add up to 6. And so we're going to constantly increase the current. That's the whole reason you're making a voltage here. Remember, you can only get a back EMF when there's a change in the flux. The change in flux can only come because it's changing within itself. And it's only changing within itself because the current is changing. So the current has to constantly be changing. And so as it's constantly changing and it's constantly getting bigger and bigger, the voltage on the resistor is going to get constantly bigger. Which means the stuff that's left over is for the inductor, because the total has to add to 6. And so if I made a plot of this, I would have this exponential factor. And so without taking the time to do the calculus again, if you remember, we did a discharging capacitor. In fact, we did all the math on the discharging, and then I said, well, the charging was kind of like it, and we just didn't have time, so I gave you the answer. And I'm going to say the same thing here, that the current then, as a function of time, would follow this 1 minus e to the minus t. And there is a slight difference here, and it's kind of the reverse. This would be an L over R or R over L? Let me look here. I think I want to say L over R. But now I'm questioning myself. There it is, L over R. Okay. And so we have an L over an R. And so we called this the time constant when we did the capacitor. Now that we're doing the inductor, I'm still going to call it a time constant. It's just our time constant before was the two multiplied together. Here, they're divided. And so let me finish this off by saying this would be the maximum current once it builds up. And you can see that the maximum current would have been what I think most of you would have thought before this chapter. Before this chapter, if I just told you you took a wire and made a bunch of loops and then a resistor, you would have just said, oh, there's no resistance there, so you would have said the current is just V over R. And I would say, yeah, if you ignore magnetism, it is V over R. But not ignoring magnetism, there is a small transition that doesn't take long, but that's what we mean by the inductance, the self-inductance. And I went to set one of these up, and I think I can still have enough time to show you. I just might not have time to show you section 11. Let me switch it over to this fun little machine. But this machine, called an oscilloscope, measures voltage. You might even see that it says 2 volts. So between each set of lines, it's a graph. Every 2 lines is worth 2 volts. And if I just measure the voltage where these wires are going, so I'll just kind of hold them in the air. Let me measure the voltage right now. Ready? Go. There it goes. I measured a bunch of zeros. Made sense, right? Nothing's hooked up. And so it just gave me a nice little 0 across here. Now the horizontal axis measures time. It's a short amount of time. 100 nanoseconds per division. Okay, and there's 10 divisions across here. So this is measuring the voltage for 1,000 nanoseconds. That's 1 microsecond. So I'll do it again here. So here's my little instruments. I will get ready. There it goes. Measured at 0 for 1,000 nanoseconds across there. Okay. Now, what if I do this? What if I actually try to hook up that circuit? So here's my battery. Here's my voltage, 6 volts. As the picture says here, let me take my 6 volts right here, and I'm going to feed it into my inductor. And so here's my inductor. I will then feed that inductor to a resistor. Now this is just a bunch of wires inside, but it allows me to turn and get whatever resistance I want. And so during the break I set it up, and I just set it at 1,000 ohms. Okay. So if I connect them together, I would say the current started rushing through here. And while it was rushing through, it was changing the current from 0 up to some value. It would be 6 divided by 1,000. And of course, now it's stabilized. So now we've reached that part of the graph where it tapers off and says, okay, no more current. But there was a transition. There was a transition where, for a moment there was a little kickback. It was having a magnetic effect on itself. And that magnetic effect makes an electrical effect, so it affects the current itself. So the current doesn't just all of a sudden skyrocket from 0 to 6 divided by 1,000. It doesn't do this. You know, it doesn't just go 0, 0, 0, 0, 6 divided by 1,000. It has some feedback. It has a magnetic effect. And that can have some interesting consequences. And these are called then inductors. And so let me see if we can kind of capture it with this machine here real quickly. And so let's see, I'll hook one wire here and one wire here. Let me disconnect them. Let me reset everything and say, all right, what if I connect them together? I will see that I connected them right here. 1, 2, 3, 4, so about 400 nanoseconds. The current was increasing in such a way that it made its own EMF for at least during that time while the flux was changing. So you only get this while things are changing. Now maybe I have to call it quits here because we're out of time, but the next section then is it would say, how could we use this piece of technology? And that's, I guess, where we'll fall short. Maybe I'll add a supplemental here too, so you can see it. But I will say your author does a good job on that last section there. All right, so I will call it quits and start cleaning up my gear, start getting out the lab, and I will see you guys in lab at 11:10 again. All right, take care.